Hi, people on Zoom. Go to the quiz. Hi, people on Zoom. Go to the quiz. All right, hi, new people. Go to the quiz. All right. And I think kind of someone on Discord asked for the quiz marks. I think we ended up saying that, like, if you did the quiz for every one of the quizzes so far, I'm not saying about the future, but so far the rules were if you did the quiz, you got full marks. So that's your marks for the quiz. And then the quizzes are best 8 of 12 as per the syllabus. So not that honors, I would say. Me make myself a little bit quieter. The questions in the quiz, though, were designed to make you kind of think a little bit. So let's go back to this. So just very quickly, you do something like this, right? So whatever, like result is 1. And then for I in range n, you multiply the result by x and you return result. So what's the runtime complexity of this? Well, you would just say, okay, so if I'm careful, and I believe I did that on the quiz, I said res is 1.0, then you would say, okay, like this is a multiplication of 2 floats because one of them is a float, so the other one is a float as well. Or rather, the result is a float as well. So float multiplications are constant time. And that means that what do we have here? Well, we have n float multiplications. And we do it. So that means that the runtime of this is going to be proportional to n. So that means that this is O of n. Or we could say proportional to n. So if you're being kind of very finicky, you would say, hey, but like, isn't n an integer? And isn't it the case that if n becomes like really, really, really large, then adding 1 to n every time would take more time? And the answer is, well, yeah, you would be correct. However, that would be a very tiny change, which I'm comfortable saying we can ignore. With that said, yes, like technically you would say it's like a tiny little bit more than O of n, because as n gets larger, like what would happen? We would need to like actually look at how the thing is stored in memory. But the reason it would happen that adding one more would take more and more time is that what happens is, sorry, quiet please. Or I'm putting this on the exam. So I won't. But so what happens is n is stored somewhere in memory, and you keep adding digits to it because you keep adding one, so at some point n grows. So that's fine. The problem is at some point you run out of space where you were storing n and you need to move it somewhere else because all the digits need to be stored contiguously. And that gets harder and harder as n gets larger and larger. So that's what takes the time when you increment n by a lot, is you try to find a contiguous space in memory where you can store all the digits of n. And the way you do it is you just look through the memory and say, like, is there a space for this huge n that I have? And it becomes harder and harder to find the space, so it takes longer and longer. So that's like the main thing. But anyway, that we can comfortably ignore, and you can always comfortably ignore, like, what is that? Well, you can say it's proportional to n, that's fine. Like, you just need to worry about, is this kind of thing proportional to n? So here's the other one. So that's the recursive version, so that's Q3. So how do we write it? Well, we say, okay, so if n is equal to 0, we know the answer. Anything to the power of 0 is 1, except for 0, whatever. So we return 1. So 0 to the 0 is not defined, but you can say, okay, like for our purposes, we'll return 1 for 0 to the 0. And then we'll say, okay, so what is x to the n? X to the n, one way of saying it is it's x to the power of n minus 1 times x. So that's what we'll do. We'll say return x times power of x n minus 1. Right? So this is just the Python way of expressing this. So now, what's the runtime of this? Well, in order to know what the runtime of this is, you actually need to look at the code tree, right? So, and again, we're going to be careful and return 1.0 so that we don't get into integer multiplication. So you start with n. The x doesn't really matter because the x is constant. And then you make a call with, sorry, epsilon 05, you're extremely happy. And then we have n minus 1. And then we have n minus 2 and so on, up until the point where we get to 0. So what I'm representing here is you make a call x to the n. In order to compute x to the n, you need to compute x to the n minus 1. So that's this call. In order to compute x to the n minus 1, you need to first compute power rack x to the n minus 2. So that's this call. And then we say, okay, just like here, every iteration took the same amount of time because what you're doing inside the iteration is you're just doing one multiplication and storing the result back. Here, inside every iteration, you check, is n equals 0? No. And then you compute x times whatever this returns. So again, every call here takes the same amount of time. And in total, we have n plus 1 calls. Because n minus 1 and so on down to 0. The 0 is the extra 1, n plus 1. Right? So we have n plus 1 calls. And we have each call takes the same amount of time. So therefore, runtime is proportional to n again. And so the plus 1 doesn't matter because O of n is the same as O of n plus 1. So technically, it's like n plus 1 calls. So the runtime is proportional to n plus 1. But for very large n, the limit of n plus 1 over n is just 1. So we ignore all the lower order terms. So here the lower order term is plus 1. You can technically say like proportional to n plus 1. so proportional to n for very large n, because for very large n, there's no difference between n and n plus 1. All that matters is the higher order term in this case. So the runtime here is all n. So the quiz was, of course, like best one of 3. So I felt comfortable asking you to think about it a little bit, even though you haven't done it yet. But here we are. So that's all then. So, okay. And this technically is not exactly the same computation because, again, if you remember the lecture from last time, here we're doing the computation going up the tree. We're doing n minus 1. And then we're also doing the multiplications going down the tree. So technically, you could say it's not exactly the same, but, and here you could see, like here, we're not explicitly using this idea of x of n, x to the n is equal to x to the n minus 1 times x. But it's quite similar. So here's an idea for how to do this more efficiently. So this is true. So x to the n is this much. But what's also true is that x to the n is x to the n over 2 squared. Right? Just because that's how powers work. Is if you want to compute x to the 4, you can say, well, that's x squared squared again. And this is much, much faster, right? The reason this is much faster is because if you want to compute x to the n, well, you compute x to the n over 2 and then just square it. And that gets you down to x to the n over 2. From that, you can get to x to the n over 4. And then x to the n over 8, and so on. You'll get to x to the 0 much, much faster that way. Right? So let's write it out. So this is equal to, again, we're just saying what's x to the n over 2? Well, that's x to the n over 4 and then squared. So that gets us to x to the n over 2. And then we square it again. And that in turn is equal to what's x n over 4? That's x over n over 8 squared. And now we need to square it again. So I'll enclose it in parentheses and I'll square it. And so on. So the other thing we could write as x to the n is equal to x to the n minus 1 and then times x. And that, again, we just kind of do the recursion manually, right? So we say, what's x to the n minus 1? It's x to the n minus 2, and then times x, and then times x, and so on. So the reason I'm saying that this is more efficient is that this is a lot fewer steps, right? So how many steps is this? Well, basically you go from n and then, so we'll need to fix it up a little bit because n might not be divisible by 2, but you go from n to n over 2 to n over 4, and so on, and you go down to 0. How many steps is that? Well, approximately log to n steps. We already had this. Yeah. Will we ever get to 0? Well, sure. If you divide, so if you divide by 2 with integer division, then yeah. So yeah. So like if not, then like yeah, you're right. It's gonna be kind of a fraction every time. It's not gonna get to 1 either. And if you do it like this, well, this is approximately n steps. Okay. And as we saw, log to n is like a lot less than n. So if you're thinking about computing whatever x to the million, you're going to have problems usually because you're not going to be able to store x to the million because that's a very large number. But this would be kind of 20 steps versus a million steps if you're talking log to n versus n steps. So this was kind of the rough idea. Now, how do we implement it exactly? So like you said, we're not actually going to get to 0 or not going to get to 1 if we're doing exact division, usually. So what we're going to do instead is we're going to say, okay, so what is it exactly? So if I'm saying x to the n over 2, like this, where this is integer division, so rounded down, and then I still want to square it, am I going to get back to x? Well, yes, if n is even, but no if n is odd. So if n is odd, then we multiply by x in order to get back to x. Right, so we're just saying, okay, like if n is even, then this is exactly true. We just multiply by 1 and it's true. If n is odd, then we're missing an x, so we'll just multiply back by x. Does that make sense? So let's now just write it in Python. So that's going to look like this. So this is going to be power recursive Charlie 06. All right, so there are tables in the front. There have been complaints that people cannot hear in the back. I really do not want to do it, but the compromise is if you cannot hear in the back, I invite you to come to the front. And if you see people coming to the front, well, feel some shame and stop talking. Okay. And just because nobody's doing it doesn't mean that you get to talk. Okay, like I know it's Friday. Do you have anything Friday 5 or are you going home after this? Oh, you have SIB. Okay. Oh, so the office hours actually start at 6 then. Okay. Sorry. So we're doing this. Are you talking during SIB as well, or is it just me? Actually, probably some people have SIB, some people don't. And so the office hours are 5:30 as announced then, or like 5:20, whatever I said. Okay. So power recursive fast. So this would be xn. So the idea would be like this. So we'll say, okay, so if n is equal to 0, I'll return 1 because x to the 0 is definitely 1. So here, what I'll do is I'll play it safe and I'll say if n is equal to 1, return x. And the reason I'm doing this is that sometimes I'll just call it with x to the 1 and I want to get x back. Unlike before where I was just doing x to the 0 anyway in the recursive call, here it's going to be more complicated. So just kind of to not make things complicated, I'm saying if n is 1, I also know the answer. The answer is x because x to the 1 is equal to x. And what I'm going to do now is I'm going to say, okay, so half power is power recursive fast x to the n over 2. And now there's two situations. So one situation is n is even, in which case I just need to return half power squared. So if n is even, it's half power squared. And if n is odd, it's half power squared times x. Right? And I'm done. So what is that going to look like? So I'm calling it with n. And then like basically approximately it's going to be n over 2, maybe a little bit less, but basically n over 2. And then it's going to be n over 4. And then it's going to be n over 8. and so on until you get to like either 1 or 0, depending on your look. So here we have log2n calls. We again need to make sure, okay, every time we call power rec fast, what happens? Well, we check if n is equal to 0, if n is equal to 1, that's not difficult. We compute half power. So that's one call. And then outside of the one call, we're just doing, well, like either one multiplication or two multiplications. So we're doing at most two multiplications. In the worst case, we're doing two multiplications every time. So that's also constant. That's all, because like square is just half power times half power. So that's also constant time. We'll have situations where it's not the case that every call is constant time. In this case, it is because it's at most two multiplications. So that's constant. So each call takes constant time. So O of log n runtime. And again, we don't need the 2 in the log2 because all the log2n is proportional to log3n, proportional to log10n, proportional to log en. So much faster. You can do exponential. There's other ways to do exponentials as it happens that are also fast, but you can do exponentiation in log time this way. So we say in log time, it's log n. Okay. So this is like so that's like this. So I want to point out that a very small subtle change is going to change how things work. So let's think about this kind of function. So I'm just copying and pasting to a new file. So let's say that instead of doing this, so I just say half power is this. I'll just say, okay, so this is like this. And otherwise, I'll say this is like this. Right? So in a way, this is kind of more natural because I'm not kind of using any math at all that they know about other than the formula. I'm just saying, well, just keep using power rec fast for anything. So that seems like the same trick. And kind of when I showed it to you with the formula, when I showed this thing, I just said, well, that's got to be log2n steps. And if you think about it with this implementation, that's misleading because this is not at all log2n, right? So what is that going to look like? Well, you start with n, and in order to compute power rec fast n, you need to make two calls. So you need to compute this, and then you also need to compute this. They happen to be equal, but the computer doesn't know that. So it's going to say, okay, like we make one call, so that's the call to n over 2, and then we're going to make another call, so that's another call to n over 2. And then this is also going to make two calls. So one call with n over 4 and another call to n over 4. And so on like this. And we're going to stop, let's say if we're lucky, when everything is 1. So here, again, each is outside of the recursive call, we're just doing kind of at most two multiplications. So each call takes constant time. But how many calls? Yeah. No. So, and other guesses? Like, so yeah.
Like the sum 1 plus 2 plus 4 plus 8.
It is. How much is that? There, well, yeah, so the geometric series, yeah. Okay. So the trick here is, like you said, we want to count up all the codes. And what we'll do is, I think exactly your idea is you're going to say, on the first level, we have one code. On the second level, we have two codes because n/2 and n/2. And then this code, so the code to x to the n/2 produces two more codes, n/4, n/4. And then this guy, I didn't type it out because that's going to be a lot, even though it's not 2 to the n. That's also 2. So in total, on this level, we're going to have 4 codes. And then in total, on the next level, each n/4 code is going to produce 2. So 2 times 4. So the next level, there's going to be 8. And we're going to keep going like that. So how exactly are we going? So we're saying 2 to the 0, that's the 1, plus 2 to the 1, plus 2 to the 2, and so on, plus 2 to the k. What is k? Where k is the last number. So we're going here on level 1, it's n, and then on the next level, it's n/2, and then on the next level, it's n/4. So it's again log to n steps to get to the top. Right? So here we are at the first step, the second step, and so on. So how long until we get to 1? Well, log to n. Right? That's how many steps. Does that make sense with me? Okay. So with this being the case, we still need to compute the sum. So this sum is going to tell us how many codes in total are there. So this picture, every number there is a code. We counted up on each level how many codes there are. So 1 here, and 2 here, and 4 here, and so on. And we said here it's going to be 2 to the k, where k is log to n. And we want to know how many codes in total, so we want to add all of this up. So this is the second formula that you should know. So this is the sum of the geometric series. And this goes r to the 0 plus r to the 1. Sorry, actually. And so on, plus r to the m is, so I'm using m because we used k and n for other stuff as well. And that's usually written as 1 minus r to the m plus 1 divided by 1 minus r. That's just a formula. So this is called the geometric series. How many people have seen it? I imagine like half. Yeah, something like that. Anyway, well, no, like actually all of you have seen it now. Okay, so here we just compute it. So this means that this is 1 minus 2 to the power of log to n plus 1 divided by 1 minus 2. Right? So I'm just plugging it in. So r is equal to 2. And then m is equal to log to n. Just plugging it in. So this conveniently is minus 1. So this would be equal to 2 to the power of log to n plus 1 minus 1. This would be equal to 2 times 2 to the power of log 2n minus 1, which is equal to 2n minus 1. So this is the total number of calls that this function that are made when computing this recursive function. So O of n. Make sense? Okay, let's do one more. Sorry, so questions about this? What's Discord saying? You're welcome. So yes. I mean, it's kind of so asymptotically, it's proportional to the same. Whether it's kind of slightly faster or slightly slower would depend. But basically, it's proportional. It's a lot slower than the log time. So just because two algorithms are O of n doesn't mean that they run in the same amount of time. It could be that one runs in time that's like 1,000,000 times n, and one runs in time that's just 100 times n. But here, like I would say comparable, you would have to, like, it depends on the details of the implementation, might even theoretically depend on the computer. So, okay. It is so it is like you would say it's more calls. It's like 2n minus 1 calls compared to n calls. The calls themselves, like probably they take about the same amount of time. It's like 2 multiplications plus some other garbage. But like it's basically comparable. So okay. So yes. Why is it I mean, that's, well, like for one, like r to the m is over here, so it's got to be larger. No, because it ends with r to the m. So like if it ends with r to the m, like if it ends with 2 to the m, it's got to be like about 2 times that in total. So okay. So that's like that. So that's like this. Sorry, quiet, please. So okay. So here's another way of computing powers, and that's like a really bad way. So I can also say that 2 to the m is equal to 2 to the m minus 1 plus 2 to the m minus 1. Right? Like that's true. So let's make a function that's based on that. So what do we say again? So this is just 2 to the m, 2 to the n. So we again say if n is equal to 0, return 1. If n is equal to 1, return 2. So this is just 2 to the n, not x, because like we want to do it in a very silly way. So otherwise we say return power 2 n minus 1 plus power 2 n minus 1. That's legit. Like it's true. 2 to the n is equal to power 2 n minus 1 plus power 2 n minus 1. So now that gets to your 2 to the n. Right? So we start with n, and then now we can't do it like this. Quiet down, please. Quiet down, please. No, like seriously, guys. So Charlie 06. Charlie 06. Yes. Hi. Okay, I can't see. Are you Epsilon 08? Epsilon 08. Hello. No, you're still talking. Epsilon 08. Yeah. No, you're still. Epsilon 08. Hello. Please stop talking. Yes, that's you. All right. So we're here. So n makes two calls. So one to n minus one, and another one again to n minus one. And then this makes two calls. So n minus two, and again n minus two. And similarly this. If you know about exponential growth, like you can see that I'm going to be running out of space very fast here. So I'm not going to be able to complete the tree because each call spawns two more. So that's going to be like this. And then eventually I'll get to like 1, 1, 1, and so on. And in fact, it's going to be extremely wide. So again, let's do it level by level. So here we have 2 to the 0, aka 1. Here we have 2 to the 1. Here we have 2 to the 2. And so on. And eventually we get to 2 to the k. What's k in this case? N. Right? Because we're counting down from n to 1 from the bottom to the top. So that means that going from top to bottom, we're counting from n of course, n down to 1. So, okay. So that means that in total, we have 2 to the 0 plus 2 to the 1, and so on, plus 2 to the n calls. And that would be equal, again, plug in the formula. So 2 to the n plus 1 minus 1 divided by 2 minus 1 is 2 to the n plus 1 minus 1 equals to 2 times 2 to the n minus 1. So this is O of 2 to the n. Make sense? So that's also extremely slow. So the runtime is proportional to 2 to the n, which grows extremely, extremely fast. So even if n is relatively small, that's going to be extremely, extremely slow. So one thing that's kind of interesting to see here is, so this is like all of 2 to the n. On the other hand, this was all of n. So why is it all of n? It's like a lot smaller than 2 to the n. Well, it's because you run out of levels here so fast that you don't manage to get anywhere. And that's because you just have log to n levels. That's very few. So it's like so few that even though you have like 1, 2, 4, 8, you don't get anywhere. Another way of saying it is just so because you have exponential growth here, so 1, 2, 4, 8, and so on, half of all the calls are on the last level. Right, so that was your question from before, why the n plus 1? Well, it's because like the last term is almost half of everything. Right, so if you're thinking about this sum, which is equal to 2 to the k plus 1 minus 1, the last term is like half of the entire sum. the reason it's half the entire sum is because it grows so fast. So this turns out to be, using the computation, O to the n. This turns out to be O of 2 to the n, which is much slower. Of course, like this is just for the sake of the example, nobody would really do things this way. So, okay. So that's like this. So I want to do one last situation. But before, sorry, question. Yeah.
Question about, the other.
Yeah.
The class where we control log 2n.
Yes.
The one above. It only works for integer powers of n because if n wasn't an integer, then you can't just add.
Yeah, so that's a good question. So the question is like the fast way of doing things where we used the repeated squaring trick that only works for integers. Yes. So one thing you would say is like, what does a fractional power even mean? So you actually need like hardcore calculus in order to define it, right? Because like in general, the way you would do it is you would say like, you didn't do it in calculus, I don't think yet. So how do you define a fractional power? Well, like you would say like x to the like 2/3, it's like the third square, like the cube root of x squared, right? Well, that's nice if you have a fraction. What if you have like a decimal? And the answer is like there are ways of computing it, of course, but like it's not trivial how you would even define it. In general, like you of course can just take the log, and like the log is more straightforward, and you would just say like 2/3 log x or something, and then you exponentiate it back. The exponential, how do you define it? Well, the answer is power series. I don't know if you probably haven't done that yet. So the answer is like for fractional power is like there's lots of issues, but yeah, like you wouldn't do it like this. So okay. So just as a preview of what's coming on Monday, the Fibonacci series, if you haven't seen it, is like this. So the idea is you take the last two terms, you add them up, and that's the next term. So 2 is 1 plus 1, and then 3 is 1 plus 2, and then 5 is 2 plus 3, and so on. So people usually define it as like fib of n is fib of n minus 1 plus fib of n minus 2. So that's what they said, right? Is basically you're saying take the last two terms and that's the next term. Take the last two terms and that's the next term, right? So and that appears kind of like in all sorts. So I'll show you some pictures that appears in like all sorts of surprising contexts in nature as well. So yeah, so how would you define it like in Python? Well, you could say return fib n minus 1 plus fib n minus 2. And here we'll just say like if n is small or equal than 2, to just return 1. So like 1 is 1, 1 is 1, and then 3 would be fib of 1 plus fib of 2. So what's the complexity of this? So you kind of start with fib of n, and then you go to fib of n minus 1, and you'd also go to fib of n minus 2. And then from here, you go to fib of n minus 2, and so on. And then here, eventually, you'll get to 1. And here you'll also get to 1, but that's going to be shorter because fib of n minus 2, it's going to call fib n of n minus 3 and also fib of n minus 4. And here you'll also get to 1, but you get there twice as fast on the right branch than on the left branch. And then there's like intermediate stuff. So as it turns out, there is a way to exactly say how many calls there are there. It's gonna be, well, like slightly surprising. So as it turns out, it's approximately fib of n calls. A surprising fact. So we'll see that next time. So for now, kind of as you're reviewing, because the exam is coming up, this might look, and in a way it is kind of a lot of information coming. But really what you need to know is you need to know, so 1, 2, 4, and so on up to n is log to n steps. You need to know arithmetic series and geometric series. And then you need to know approximately 5 common shapes of goal trees. So so basically we've had like the different trees. So we have this kind of thing, which we'll see on Monday. And we had this kind of thing. So branching and going n minus 1 and so on. So that's 2 to the n. And then we had this kind of thing where there is branching, but we just have log to n levels. And then we had kind of the straight trees with n minus 1 and so on with n calls, or the one with log to n calls. So that's, I counted, well, I think like 6. So as you're reviewing, just systematize it, right? So just like look at it and say, okay, like those are the kinds of trees that they looked. That's most of the prior exam questions. Of course, like sometimes I get creative, but I'm not that creative. So just systematize it, write it down in your notes, and it's going to be fine. All right, I'll see you. So I have office hours as announced on Piazza starting in 20 minutes now, and then Saturday and Sunday, and then I'll see you Monday. Bye. Which one?
Just the one that you're saying about. Yeah.
Yeah.
That is- Thanks.
So this, by the way, it's all recorded, right?
Oh, yeah. Oh, yeah.
Yeah.
Have a nice day.
Bye. Yeah.
So this one here, the cover, and that is so when you sit it against.
Well, I mean, the one you show, the 4 loops, but that means that it's great. That's
Sorry, This trees.
Yeah. Well, so 5, I said like approximately, but yeah. But then one of them, so one of them is kind of straight n minus 1 and minus 2. One of them is like n over 2 and over 4.
It's like 4 loops, it's a small 4 loops, it's like n, and then that's like to the power of the pound. I know it's lots to n. And then there's the first is like, I guess like you put us 20 different kinds.
Yeah, something. Well, I would say I showed you like 5 different, but yes.
Okay, I kind of got lost. Is this O log n? There's a log 2.
So O log n and O log 2n are the same thing because logarithms are also yeah. All right. Yeah. No, line means you're not. So you know that or like you know. All right. It might be that it's the okay. So that means which two? I mean, I think like if you know who it was, that if not, Yeah, just email me and with your name.
Okay.
Yeah. Yeah, so I think we should go outside, yeah. Just 1 second. So I would, thank you. No, thank you. Thanks very much. Yes, I'll just go outside then. 5:30. Oh, when is it ending? So I'll just wait until the last person leaves. So, yeah, so
Ambitious.